Okay, you ready? Okay. Oops, I'm not ready. Okay. So today is gonna be the new topics. Okay. So in the past, we can see that we encounter with solving the system of linear equation. Okay. If you do the least square problem, least square method, you will see that suppose that we have data. Okay, and we want to see the trend. If we say, okay, I try to find the least square of linear, we will have equation y equal to a plus bx. But if we want to find the polynomial of degree 3, for example, you're going to have y equal to a plus bx plus cx squared. Okay. And if you say, okay, maybe the data that we have is the polynomial degree 5, okay, you will have y equal to a plus bx plus cx squared plus dx to the third plus ex to the fourth plus fx to the fifth. So how many unknown that you want to find? You want to find a, b, c, D, E, and F, which is 6 unknown. Okay, 6 unknowns. This means you have to find the error function, which depend on A, B, C, D, E, F. Okay, error function. In order to find the least square error, we have to set up the 6 equation with 6 unknown. Okay, by setting that partial derivative with respect to a equal to 0, partial derivative with respect to b equal to 0, c equal to 0, six equation, 6 unknown. Okay, 6 equation and 6 unknowns. So we will need to find tools. We need to find tools to solve for 6 equation and 6 unknown. If we do by using the elimination method, it's gonna take you quite a long time to do it. Okay. When I say the 2 equation and 2 unknowns for the let me write down system of linear equations. That, for example, when you have ax plus b bar. For example, this is what I said by 2 equations and 2 unknowns. 2 unknowns are x and y. 2 equation, I call this equation number 1, I call this as equation number 2. The first way to solve this 2 equation and 2 unknown is like elimination, right? You try to make the coefficients of the equation to be only 1, okay? So the first method is called elimination method. So you have equation 2x plus 3y equal to 2 as the first equation. And if you want to get rid of x, okay, I will multiply equation number 2 by 2 over 3 times equation number 2, okay. If I multiply 2 over 3 to the second equation, I will get 2x minus 2 over 3 times 6y equal to 2 over 3 times 3. I get equation number 3. I rewrite it as 2x minus 4y equal to 2. That's number 3. Okay. So I have 2 equations and 2 unknowns. Okay. Let me erase this. So then I have the equation number 1 and number 3. Okay. Then I have equation number 1, subtract equation number 3. When I subtract, you change the sign. So I get 7y equal to 0. This means y is 0. And then I substitute x plus 3 times 0 is equal to 2. So x is 1. So you know the solution is x equal to 1, y equal to 0. This is a substitution. Okay? This is the first method. The second method that I think I teach you like called the Cramer rules. Okay? I have 2 equations. These 2 equations can be written in terms of the metric metaphor. Okay? As the quotient matrix 2, 3, 3, negative 6, multiplied by vector x and y equal to 2 and 3. Right? So you can rewrite this system of linear equation, which is the same as this form. Okay? When you do this is the matrix 2 by 2. This is the vector 2 row and 1 column. When you do the matrix multiplication, you look at the resultant matrix must be 2 by 1. Okay? So you will say that, okay, now, if you want to get the first one, you take the first row multiplied by this column, you get 3, 2. So you get 2x plus 3y, okay, on the left-hand side. The second one is the second row multiplied by this. Second row, you get 3, 6 here. You get 3x plus 6y. Equal to the right-hand side is 2, 3. Matrix on the left-hand side has dimension 2 row and 1 column. On the right-hand side has 2 row and 1 column. So the matrix equal to each other means each location must be the same. Okay? So it's gonna be 2x plus 3y equal to 2, 3x plus 6y equal to 3, which is the equation that we have. Minus 6, thank you. Minus 6, thank you. Okay, so it's minus 6y equal to 3. So you have these two equations. So you should be able to rewrite, okay, this linear equation, system of linear equations in terms of the matrix vector form. Now by the Cramer rules, to find x, you use the determinant of the matrix. Okay, determinant of 2, 3, 3 minus 6. And then the top numerator, you replace this to the first column. Okay. You see the same thing, okay? But let me just show you how to find the determinant of the matrix. You get minus 12 minus 9. X is 1. Okay. How about y? Zero. Okay. So you get y equal to 0 and x is 1. The same thing. You get the same thing. Okay. If you have equation, system of linear equations, never say A11 x1 I have first equation. All those A here, A11 is number, 12 is the number, 3, and, okay. The first number here, number 1 here, is represent the first equation. First equation of the coefficients of the first unknown, A1. Second unknown, x2. Third unknown, x3, and unknown, xn. In the second equation, I will say A21 times the first unknown, x1. Second equation of the second term, A22, x2. Second equation, third term, x3. Second equation, xn. Now, if I have the last equation, I will say what? A n1 x1, a n2 x2, a n3 x3, and so on, plus the last equation, the last unknown, times the last right-hand side. Okay? If I rewrite this in terms of the matrix vector form, okay? It's just the coefficients of the matrix multiplied by the unknown vector equal to the right-hand side vector. So I give the name for this matrix capital A, okay? In the general form, we write down if you call the matrix capital A, the entry or the element of the matrix is represented by the lowercase a. The first index of A is gonna be tell you the row. The second one would say the column, okay? So I call this whole thing as matrix A. The matrix A has element, actually I should have the comma, okay? But just too much. It just have to be 1, 2, and so on. But I write here is 1, 1. Everybody know it's mean A at the row number 1 and column number 1, 1, 1 here. The right way to write down is A1, 1. Okay? Or A1, 2 is mean the element is located at the first row and the second column. A4, 5 mean the fourth row, fifth column, okay? So you will see that like, this is matrix A. And in general, the vector X in the book, they can use boldface, the thick one. But I use X with this notation. Okay, arrow on the top represents vector X. Vector here is called a row, column vector. Vector is the matrix which has only one column or one row. In general, if you have one column, you call column vector. But in short, they call it vector. So you know that this is the vector X. Okay? And vector X has n row and one column that I mentioned. Okay? And the right-hand side vector here, I call it as vector B. Okay? So from now on, I will say that we will try to solve the system of equation as AX equal to B, where A is the quotient matrix. And to be precise, A is the square matrix. In row and in column. This is what I mean by the square matrix. Okay. So number of row equal to the number of column. So this is called the square matrix. Can write down as 3, 5, 4 minus 2 and x, y equal to 5, 3. So this matrix is A. This I call is vector X. This I call vector B. Okay? If it's 3 by 3, maybe like this. So if you write down in terms of the matrix vector form, you will have to arrange this 2, 3, 0, Z, X, Y, and Z. And the right hand side, so the first row multiplied by this column, you have to transpose, okay? So you have 2x plus 3y plus 0z equal to 5. The second equation, you will have 1x minus y plus 1z equal to 2. The third equation, you have 4x minus 2y plus 6z equal to 1.32. You see, actually you take array the x, y, and z, and these are coefficients 2, 3, 0, 1 minus 1, 1, 4 minus 2, 6, okay? So this is just the matrix multiplication. So you guys can review. Okay. You can search on the internet, teach me how to do the matrix multiplication. Let me do it. Okay, there are so many of them. Okay, you can do the quick review of how to do matrix multiplication. This they will tell you one by one. They will teach you how to do matrix multiplication. You can find the resources from the internet. So many places. Okay. Okay. Now, for 3 by 3, to find x, y, and z is still something that we can do it by using what we call the elimination, okay? Elimination. But if it's larger than 3, 4 by 4 is kind of difficult, okay? And the geometry of 2 equations and 2 unknowns, okay? I can tell you that. If you have 2 lines, okay, it means you will see the intersection of the point. Suppose you have these 2 equations and 2 unknowns. The solution of the system of linear equation is when you try to find the values of x and y that satisfy both equations, okay? So it just basically the intersection point of those 2 lines, right? Because at that point, at the same time, they stay in both lines. So that is called the solution. But there are only 3 cases, okay? 2 lines cut at one point. The 2 lines is exactly the same, okay? These 2 lines, which is exactly the same. You can see y equal to minus x plus 4 and 2x equal to minus 2x plus 8. So this actually they are the same line. So the solution is every point along that line, right? So you in this one you will say that is the infinite number of solution. And the infinite number of solution, which means they are all the values x and y that stay in that line, okay? And the other one is called no solution. No solution is mean like you have 2 lines which are parallel to each other. No intersection point for these 2 lines, okay? So this kind of no solution. There are going to be only 3 cases only. 1 solution, 2 lines cut at one point, no solution, parallel, and exactly the same line. These are called the infinitely many solutions, okay? So it's going to be all these 3 cases. But now we will focus only on the case that we can try to find 1 solution, okay? 1 solution. This is for 2 equation and 2 unknown, okay? If you think about 3 equation and 3 unknown, this is the picture, okay? I cannot draw this, but I want to show you the first one. You can see 3 equation and 3 unknown. It can be represented by plane, okay? Each plane represent each equation. If those 3 plane intersection at one point, the one on the corner with the yellow dot there, it's called the solution of this plane, of these 3 equations, 3 planes intersection at one point. So you have a unique solution, 1 solution. But the second one, you might have 2 planes parallel to each other and 1 plane cut. So you will have 2 lines, okay? 2 lines. So those 2 lines parallel to each other. So this is no solution. okay, because no intersection point. But if those three planes, I would say if three plane, this picture is not the picture I want to say is like three planes lie the same place, okay? So it's infinite many solution. But if those three planes no intersection, or like this one is the other things is which is you might we say that the system is inconsistent, okay? This consistent and dependent is mean that it's no cut, okay? No common cut at all. So you will say that it is the consistent or the is dependent system, okay? It's not, it's dependent system. But if you have two plane parallel and one cut, okay? Two plane parallel and one cut, so there are no solution. I will go to this one later, okay? Because it's not easy to visualize, okay? But the things that I will say here, and I try to go from this line and plane, and you can think if I have four unknowns, we cannot visualize the solution. At least if you have three equation and three unknown, you will see at least the possibilities of the solution, okay? If they might have cut only one solution, or they have no solution, or you have infinitely many solutions, okay? But if you have more than 3, 4 by 4, you cannot draw the picture. 5 by 5, you cannot draw the picture, okay? But now we will try to learn how to solve 3 equations, 3 unknowns, 4 equations, 4 unknowns. 1,000 equation by thousands unknown, okay? And you might ask me that why you have to solve 10,000 by 10,000, maybe in the real application, okay? They more than 1,000 by 1,000. Microsoft Excel, I think they can solve the system of equation, I think that 2,500 maximum. Okay, they can handle matrix of the maximum size 2,500. So instead of writing out the equation, suppose that I have the equation. I'll be able to write this one in the matrix vector form, right? My matrix will be 2, 5, 0, 1. If I have x equal to 1, y equal to 2, actually I know the solution. I have x equal to 1, y equal to 2. I can always write the matrix as well, okay? I can write the matrix as 1x plus 0y equal to 1. 0x plus 1y equal to 2. Okay? Or I have equation y equal to 3. 2x plus 5y equal to 2. I can rewrite the matrix as 0, 1, x, y equal to 3, 2. 2x, 5y. Okay? See. Okay? Let's see. Okay? This line is equation 2x plus 4y equal to 6. Okay? Okay? The other one is this. Okay? So you will have this equation 2x plus 4y equal to 6, which is this equation, okay? And the other one is 4x minus 2y equal to 7. Okay. So now, I will write down the equation. 2x plus 4y equal to 6. And 4x minus 2y equal to 7. I have the first equation, I have the second equation. My first equation, if I multiply by 2, what will I get? I will get 4x plus 8y equal 12. Okay? Let's see. If I draw the graph 4x plus 8y equal 12, what is going to be this one? Okay? Four x plus 8y equal 12. Actually, it's the same equation, the same line. Okay, you see, if it's equal to 1, is this line the one on the bottom? If I say 12, is gonna be the same equation. What does this mean? What I want to tell you here, okay? So you can see the two equations. The solution is the intersection point, okay? So if I have, can I have the peach color? Okay, if multiply the equation with the number, this I multiply the first equation by 2. The equation, the line, the geometry, the graph remain the same. Okay, so the solution does not change. Okay, this does not change. Okay, equation number 1 and number 3, the same line. And this means that if you want to find the intersection point of this line number 1 and line number 2, which is your original problems, if you multiply any equation by constant, the solution does not change. So it's remain the same. Okay. How about if I have number 3? Now equation number 1 and number 3 are the same. The solution of number 2 and number 3 is gonna be the same, right? That's one thing. It's been multiplied. Okay. That's not change. Okay. So is will not change. And instead of I call number 1 and number 2, and number 2 and number 1, does the solution change? It doesn't matter, right? If I call this line equation number 2, this line equation number 1, or I call this one as the equation number 1 and number 2, the intersection point does not change. Okay, it does not change. When I call the number, I swap. Okay, I swap the equation. It means it doesn't matter which equation that I call the number first, second, or third. Okay. If I write it in terms of the matrix, it means if you swap the row. Okay, you swap the row. If I multiply the, okay, let's see. I write down the matrix form. Okay, I have x minus 2y equal to 3, 2x plus 3y equal to 1. I call this as equation number 1, this equation number 2. So you will have, write down 1 minus 2 times xy equal to 3, 2, 3, 1. Okay, you can see that I swap the row. This one will interchange. Solution remain the same. Okay. Number 2. Okay, I multiply equation number 1 by 2. What do I get? I get 2x minus 4y equal to 6. I call this as number 1. And 2x plus 3y equal to 1. Okay. So my system would be 2 minus 4, 2, 3, x, y equal to 6, 1. As I show you, the graph, the line here, after I multiply by 2, and the one there, the same thing, okay? Intersection point does not change, okay? Now, how about if I have equation number 1 subtract by equation number 2, I will get what? 1 by 2. I will get minus 7y equal to 5. So y is 5 over minus 7. Okay. X minus 2y equal to 3. 2x, oh no, 2x plus 3y equal to 1. 2x plus 3y equal to 1. Okay. These two line intersection here, okay? And the equation y equal to minus 5 over 7. X minus 2y equal to 3. Oh, not 1. Plus, right? Sorry. Okay, sorry. Okay. You can see equation number 1. Okay, let's see. Okay. So this is equation number 1. X minus 2y equal to 3. This equation 2x plus 3y equal to 1. Intersection here. Okay. And the last equation, I have equation number 1 minus equation number 2. number 3 in this one. I get equation that y equal to minus 5/7. This is this line. You can see that equation number 1 and equation number 4 cut at the same point, okay? It means that you can add or subtract any two equations. The solution remains the same. It means the solution does not change. The intersection point remains the same, okay? So this is actually what you have done in the elimination method, right? Okay, so this is tell you that if you have any two equations, you can add or subtract any equation and the solution does not change. The solution does not change in mathematics. We use the word, the system of equation. We have equilibrium. Not equilibrium, I'm sorry, equivalent system, okay? They are equivalent. You have the same solution, okay? You have the same solution. Equivalent system. So I will say that this system and system okay, you can see this one is the first row. I interchange row number 1 and row number 2 of the equation and interchange the equation. They are equivalent, okay? In this one, in the book, sometimes they use this, okay? This means equivalent notation. Some book they use 3 equal sign, okay? It depends. So I think I would use only one. So lazy people. So mathematician, we are lazy people. We just don't want to, write a lot or so many things, okay? Now I also want to simplify my notation. From this one, we have the system, the system metric A times vector X equal to vector B, okay? And since we know that the unknown that we want to solve are X and Y, so instead of writing Ax equal to B, I will write down as A and B. Okay, I will write down this as 2, 3, 1. 1 minus 2 and 3. So this is just the right hand side, the quotient matrix and the right hand side vector. Okay, so we have the name for this one as augmented matrix. Just lazy to write down X and Y, so we just only write down the information that we want, and when we omit, we ignore, we do not write down the unknown X and Y, okay? Because now it's only X and Y, but we know that our goal to solve any equation and unknown, and maybe hundreds of unknowns, okay? So we will write down only the quotient matrix, okay? So we write down is as the augmented matrix. And we will say that, okay, this I will give the name as row 1. This is row 2. Okay. And when I say I want to do some operator for this matrix. I want to say that, okay, this matrix 2, 3, 1, 1, minus 2, and 3. Okay. If I want to interchange okay. So in the first one, I will write down that R1 equal to R2. It means I will replace R1 with R2 from the previous matrix. So I get 1, minus 2, and 3. Okay. And then R2 with R1, which is 2, 3, 1. I interchange the row, or that means I swap the equation. Okay. If I have this matrix, I want to get the second row multiply, okay? R2. It means that the first row I'm not gonna do anything. And the second row, I want to multiply that by 2. I multiply by 2, I get minus 4, and we get 6. It means that I overwrite the second row by 2 times every number in row number 2. Okay? It is the same as you multiply the equation by a constant 2. The same thing, but just for shorthand. Okay? Okay. For example, if I have this okay, I would say is equivalent with R2 is replaced by R1 minus R2. Okay. Where R1 is the same. R1 minus R2 is mean 2 minus 2, 3 minus 4, 1 minus 6. Okay. Okay. So just the notation that we use, okay? Actually, in theory, we call it row operation. I don't want to give so many vocabulary here, but it's just you do operate and the row by first, you can interchange the row. Number two, multiply every row by constant, non-zero constant. Number three, you can add or subtract any two rows, okay? So this will not change the solution. Physically or geometry, it means that all those lines, all the equations that are represented, they have the same solution. In mathematics, we say that they are equivalent, okay? They are equivalent. So we will use all these things to do the operator, okay? But before we go to this, I want to introduce you to some matrix which we think that is easy to find the solution. If first one is identity matrix. The identity matrix under the multiplication is the matrix that has the one along the diagonal for 2 by 2. If it's 3 by 3, you will have 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is 3 by 3. Okay, this is called identity matrix. If we have the quotient of the matrix as the identity, it means that we have the solution already, right? We have x equal to something, y equal to something, and z equal to something. Number two, I will introduce you what we call the upper triangular matrix. For example, I will have, I call it U11, U12, two by two matrix. For example, you have 1, 2, 0, 3. 3 by 3, 1, 2, 2, 0, 3, 1, 0, 0, 2. Something like this. You can see that they have the okay. You have this one. Okay, you can see this is called the upper triangular matrix. So you can see that the one below the diagonal element, the diagonal element is mean this one is the diagonal matrix, okay? Diagonal element, diagonal. So the one below the diagonal equal to 0. All of the element belong the diagonal matrix equal to 0. We call this matrix as upper triangular matrix. And the other one I will call it as the unit upper triangular matrix. Unit is mean 1. It means that if I say unit upper triangular, it means the element along the diagonal equal to 1. Okay, so instead of U11 and U22, it's gonna be 1 here along the diagonal. Okay. Okay, you can see that the element here, 1, 1, 1, 1. Okay, we will call this as the unit upper triangular matrix. Once we have upper, we have lower triangular matrix. Since I call it lower, I use the element L11, 0, L21, L22. So for example, it's 2 minus 1, 1, 0, 1, 3, 4, 0, 0, 0. No. Okay, so we have lower triangular matrix. Okay, so you have this lower triangular matrix like this. And the other one is called unit lower triangular matrix. What is the difference? The one along the diagonal are 1. Okay, so I will call it as the unit lower triangular matrix. So instead of L11, L22, we have number 1 along the diagonal. This one have to be 1 along the diagonal. This one have to be 1 along the diagonal. So this is called the unit lower triangular matrix. So these are 1, 1, 1, 1, 1, 1, 1. Okay, so these are unit lower triangular matrix. I like it. I introduced to you because we like this one. We like the upper triangular matrix and lower triangular matrix. Okay. What we try to do on Friday is I will introduce you to what we call the Gaussian elimination. For solving AX equal to B. What we try to do is we try to change the system AX equal to B. Okay. We try to use all those three operator that I told you that we can swap any 2 rows. We can multiply any row with a constant. We can add or subtract any 2 rows. Okay. We try to change this or transform this in such a way that the system is still equivalent. Okay, to something called the upper triangular matrix. That when we say equivalent, it means X remain the same, right? So the solution does not change, but the quotient matrix from A is will change to U. U here is called the upper triangular matrix. Your matrix is upper triangular matrix. The right hand side also is changed. I use B prime, is changing, but X remain the same. It's the way that we do it for the make the complex system to the easiest one, okay? Because once we do like the upper triangular matrix, we can find the solution very easy by using what we call the back substitution or backward substitution. I give you example, okay? I have X plus Y plus Z equal to 1, Y plus 2Z equal to, let's see, suppose x is 1, y is 2, z is 3. So, no, it's 6. Suppose x, y, z is 6, y is plus 2z, 7, and z equal to 3. For example, like this. If we write down in terms of the augmented matrix, okay, or matrix vector form, you will have the system as 1, 1, 1, 0, 1, 2, 0, 0, 1, times x, y, and z equal to 6, 7, 3. If I have the system like this, you can see that the quotient matrix is upper triangular matrix. Okay. On this one, this particular example, I say that maybe I can make it more like 2, 4 plus 6 is 10. Okay. So this is matrix U, upper triangular matrix. Okay. Upper triangular matrix. It's easy to find the solution, right? Because you can say that z is 3. When you know z, you plug in z here, you can get y easily. So y is just 10 minus 2z divided by 2. Okay. Now you get z and y, you plug it in on the above equation, you get x. X is equal to 6 minus y minus z. 6y is 2, z is 3, so you get 1. So you get this x is 1, y is 2, z is 3. So you can find the solution easily. Okay. So the thing is, once we have the system of equation, now, later on, even a is 1000 by 1000 by using Gaussian elimination. You can reduce this a to u. Once you have u times x equal to b, so you can use back substitution. Okay, keep repeating the same procedure until you get all the unknowns you want. Okay, but it is the systematic way to keep track of the algorithms. Okay, is doing the similar way, the same thing over and over again. Okay, you will get the system 1000 by 1000, and later on you get the last solution. You can backward to get the x 99, you get x 98, and so on. So until you get the first one, first unknown. Okay. So on Friday we will come back and look at what we call the Gaussian elimination. Okay. So you can search on the internet, look at the Gaussian elimination. Okay, so there are so many, video available on the internet. Okay, even MIT, they can also post to you. All right, see you guys on Friday. Okay, and then next Tuesday is no class. Okay, because the graduation. Okay, bye.